In the last two parts, we explored the complex world of crystals built on 4 axes. Now we are going to simplify things again and go back to a framework of 3 axes. But this time, we are going to break another rule of symmetry. What if you have 3 axes that are all at 90-degree angles, but they are all different lengths? You get a shape like a perfect rectangular brick or a matchbox. You get the orthorhombic system. Welcome to part 5 of the series. The rule for the orthorhombic system is straightforward. It has 3 crystallographic axes, which we call A, B and C. They are all mutually perpendicular, which means they all meet at perfect 90-degree angles. However, unlike the cubic and tetragonal systems, all 3 axes are of unequal lengths. So the relationship is A is not equal to B is not equal to C. But all the angles are 90 degrees. This is the system that gives us the familiar shape of a brick or a matchbox. With all 3 axes having different lengths, we have lost even more symmetry. The defining characteristic of the orthorhombic system is that it possesses 3 two-fold axes of rotation, and these axes are mutually perpendicular to each other. These 3 axes of symmetry are the 3 crystallographic axes themselves. The normal class, which is known as the Baryte type, also has 3 mirror planes that are perpendicular to these axes. It also has a center of symmetry. Think about a matchbox. You can slice it in half along its length, width and height and get a mirror image each time. That's the symmetry of the orthorhombic system. The forms in the orthorhombic system reflect its brick-like shape. We often see rhombic prisms, which are 4-sided open forms, but the most common forms are pinacoids. A pinacoid is simply an open form made of 2 parallel faces. In the orthorhombic system, you can have 3 different pinacoids oriented along the 3 different axes: a front and back pair, a side-to-side pair, and a top and bottom pair, which is the basal pinacoid. A typical orthorhombic crystal is essentially a combination of these 3 pinacoids, which together form a closed brick-like shape. The orthorhombic system is home to many famous gemstones. One of the best known is topaz. Topaz is a beautiful and durable gem that comes in many colors, but it is also used industrially to make refractory materials. This means they can withstand very high temperatures like the inside of furnaces and kilns. Another famous orthorhombic gem is the beautiful green peridot, which is the gem variety of the mineral olivine. Olivine itself is an extremely common rock-forming mineral, especially in volcanic rocks. While its main use is as the gemstone peridot, it's also used to make abrasives and refractory sands for steel manufacturing. The type of mineral for this system is baryte. Baryte is a surprisingly important industrial mineral. Because it is very dense, its primary use is as a weighting agent in drilling mud for the oil and gas industry. The heavy mud helps to prevent dangerous blowouts during drilling. What we are seeing as we move through the systems is a progressive loss of equality. We started with the cubic system, where all 3 axes were equal. In the tetragonal system, only 2 were equal. Now, in the orthorhombic system, none of them are equal. This step-by-step reduction in the constraints placed on the unit cell allows for a wider variety of atomic arrangements, but it also reduces the overall symmetry of the crystal. Each step down in symmetry opens up new possibilities for mineral structures, which is why we see so many different minerals in these lower symmetry systems. So far, all the systems we have looked at have had one thing in common. All their axes meet at perfect 90-degree angles. But what happens when we break that rule? What happens when an axis starts to tilt? Join me in the next part as we enter the tilted world of the monoclinic system, the single most common crystal system for minerals on Earth.